go.
Jesus.
I really enjoy that video. It's called Pigeon Impossible. You can. It's surprising. By the way, the see the locations down. There's no place where you can look down a street and see the Washington Memorial. The Washington Memorial, yeah. But everything else was completely accurate. Okay, we've got 15 seconds. Any final questions? The birds work for the bourgeois. Yes, right. Okay. Here we get, let's get started. Screen. Okay, today we're covering, we're continuing what we did last time, where we're covering kind of the 3D universe. Today we're going to be covering lunar eclipses. We'll talk about two different types of eclipses, and then we'll talk about what we call the geocentric and the heliocentric universes. Unfortunately, there's many different phrases for these. For example, the geocentric universe is sometimes called the Ptolemaic universe, and the heliocentric universe is often called the Copernican universe. But we'll get to that in a minute. Anyway, we'll get started again. Pay close attention because there's going to be a lot of 3D thinking about this. And again, I'll talk 60 minutes. Put your questions in the chat. I may or may not get to it during the 60 minutes, but then I'll certainly try and get to all your questions in the last 15 minutes. Okay. So here, you are going to be responsible for this. The sunlight, the sun is right in this graphic, and here are the different phases. Again, everything in the in our solar system goes counterclockwise. The moon is going counterclockwise around the Earth, and we go from a new where the moon is mostly dark to what we call a waxing crescent. Waxing, you're adding stuff. There's a little crescent there. First quarter is where we see half light, half dark. Waxing gibbous, it's still growing. Gibbous, monkey, I don't know what it means. Anyway, that's the name we're responsible for. A full moon, waning gibbous, third quarter, and waning crescent. If you think about this, waxing means getting bigger, waning means getting smaller, and makes sense. Gibbous is the only word that doesn't make any sense, so pick. Notice that the moon varies depending on the phase. For instance, the moon is directly over at noon when you can't see it. And when it's full, it's directly overhead at midnight. This quarter is directly overhead at sunset. So here's another way to look at it. And this is from perspective of the Earth, which you'll see on the right, and then perspective of the moon, if you were sitting on the moon. And here's another graphic, and you really have to just sit down and think about it, and maybe have marbles that you spin around, that the location of the moon depends on the phase. So here we're looking at sunset, and at sunset, the moon is directly overhead. But if it's a full moon, it'll be just setting, okay? And then we have the same thing here at sunrise. The location of the moon depends on the phase. So at sunrise, right there, the moon will be directly overhead if it's in the third. We'll see it setting, it's close to, and we'll see it rising when it's close to. I've got a couple of relations to show you, so we can go over that. Let's go to Safari, share. Okay. So here is an animation, and you are that person. And as we go around, notice that the phase changes with what you see, and notice the time of the day changes there, okay? And the sunlight's in this graphic is coming over from the left. And note here, this is what it looks like from your position. So this is the real position, what it appears to you. There's your horizon, there's the sun, and then there's the moon there, okay? And so notice they kind of chase each other. It takes, of course, 1 month for the moon to go around this circle, and it takes the sun 1 year to go around that same circle. Okay. And if anybody wants, I can bundle up these simulations too and send them on. Without the previous phases of the moon from the night before, if I look up the night, how do I tell the difference between a waxing or waning gibbous? Well, two ways. One way is whether it's waxing or waning on the left and the right. If it's dark on the right, then it's going to be waning. If it's dark on the left, it's going to be waxing. Okay. And the other way to tell is just the location. Okay. So where it is in the night sky. Well, if you know the time of the night, we'll tell you where the phase is. And so that should match up exactly. So the sun, cold, the sun and the moon absolutely do follow the same line in the sky. It's called the ecliptic. And we'll be talking about that throughout this entire course. Okay. Let's stop this and let me show you another animation. Let's see. Okay, so here's the sun and the moon. Let's see, reset. Okay, so there's the Earth and sun. In this case, the sun is front left. This line bisects what's going to be light and what's going to be dark, and so we'll show the shadows there. Here is the line between the Earth and the moon. Here's the bisector. These lines describe where we're pointing towards the sun. And then let's up a little bit and notice as we move the moon around, the light side, of course, always points towards the sun, but the part that we see just as we go around.
And
okay, I'm going to mute y'all, and then we can talk when we get to the QA session. Okay, so I'll bundle these simulations, put it on the resources in WebAssign, and you can play with this. Again, it's going to take some time to figure this out. Okay, so let's get back to presentation. And again, you're going to be responsible for these different phases. Hold on a second. Okay. Oh, here's a cute. Watch this. What if other planetary bodies opened our world at the same distance as the sun? We'll be coming back to these planets. Okay, so that lunar phases, and again, you're just going to have to sit down and play with it and look at it to figure it out. Now we're going to talk about eclipses. So this is where the Earth blocks the light going to the moon. We call that a lunar eclipse. where the moon blocks the light coming to the earth. We call this a solar eclipse. And when the sun is the earth and the moon, what do we call this? Anybody? Yeah, Jupiter is definitely kind of big. Jupiter is 10 times, in terms of radius, the size of the earth. So what do we call this third type of eclipse? Quentin says impossible. Total? No. Keep trying. One more. Annular? That's a good try. Nothing. Good try. Planetary? Nope. If the sun was between the earth and the moon, that means the earth and the moon are opposite sides of the sun, which means it's the apocalypse. There's just no way. Anyway, it's a physics joke. Astronomers are known to be great comedians. So a lunar eclipse. Let me bring up another. Yeah, here we go. So here's the Earth. Here's the moon. Moon goes around the Earth like that. Sorry. And notice that there's a shadow behind each of these, but it's not a sharp shadow. And the reason it's not a sharp shadow is because the sun has a certain size. The sun is, half a degree across. And notice that gets fuzzier as you get closer and sharper as you get farther away. Okay. And here is the moon. And note that at some point, the little tip of where you're actually completely shadowed, you can't see any light from the sun in this shadow. We just kiss the surface of the earth, and that would be a total solar eclipse. And now the moon goes around here and it goes into this deep shadow here, and this is called a lunar eclipse. Okay, so here the solar eclipse is this narrow line that cuts across the earth, and it travels about 2,000 miles an hour as it cuts across. Here is a lunar eclipse where the entire moon is blanketed by the much larger shadow of the earth, and everybody on earth on the night side can see that shadow. Let's go back. Okay. Can you explain the difference between sidereal period and Sidonic period? Yeah, let me get that down and I'll bring that up next lecture. I have a short little video clip on that. I actually don't quiz you on that because I think it's a little esoteric, but it's interesting to know. So here is a lunar eclipse where the moon is in the Earth's shadow. And here's a simulation of that. And so note that what we call the Earth's umbra, that's the really dark part of that shadow, is almost 3 times bigger than the moon itself. It's huge. And the penumbra is where the light has been decreased. It's that lighter part of that shadow where some of the sun is still shown. Okay. Lunar eclipses are not terribly uncommon. We see one every few years. There was one was it last year, 2 years ago? I forget. Okay. And they tend to proceed fairly slowly. I mean, this takes a couple hours, so it's not terribly dramatic, but it's still kind of neat. Okay, so first quiz. Again, this is ungraded. Let me bring this up. This is lecture 4. So at mid-eclipse, where will the moon be? Rising on the eastern horizon, setting on the western horizon, about halfway up the celestial sphere, directly overhead. And so now the question is that you're given the timing here, okay? And this is in our location. So we're going to look at Eastern Standard Time, okay? And if you look at the time, since remember the moon has to be full in a total lunar eclipse because the moon is directly opposite the sun. And so it has to be full. And so the question is, where would the moon be at mid-eclipse? And there is mid-eclipse right there. So let's launch that poll. Yeah, so the question is the moon shadow also referred to as an umbra? Well, actually, it's any shadow. Any shadow, the darkest part is called the umbra. The fuzzy part on the outside is called the penumbra. Okay, and that's not just with the moon shadow or the earth shadow, it's any shadow. Is the mid-eclipse the one under the full moon? Well, all lunar eclipses have to happen at the full moon. Mid-eclipse is where the entire moon is darkened. Okay, there is some about this, and so let's go back and look at it. So let's new share. If we go back to here, so the moon has to be right here at for a total a lunar eclipse. It has to be a full moon. And so the question is, at mid-eclipse, the time there is midnight, basically. This is midnight, where you're directly right at the center. Okay, let me go back. Shoot. There we go. Okay, so at midnight, you're directly opposite the sun. And so there you are standing at midnight. There the moon must be for a total solar eclipse. And let's try this poll again. And at mid-eclipse, it's midnight. So Austin, you're exactly correct about that. I just want an excuse to show the neat video. Okay. And that's correct. Okay, it's directly overhead. Okay. So let's go back to Keynote. And next question is, in Seattle, which would be Pacific Standard Time, where would it be? So let's see, polling. Okay, and poll. And there seems to be some debate here, so let's just take a look. Again, let's go back to the simulator. And Okay, so that is, that's about 9 p.m. So as we come around, this would be 6 p.m. There's noon, 6 p.m., 9 p.m., midnight. Okay, so there's about 6 p.m. And so there is uh, there is the full moon, which of course is being eclipsed now. And so you could say it's, and your horizon line would be a line that kisses your location here. And so this would be your horizon line right there. And so I would say probably the best answer would be either rising on the eastern horizon or about halfway up the celestial sphere. The answer they were looking for is about halfway up the celestial sphere, but it definitely is, it's later, but it's rising, as you can see. So if you see it, in fact, you can see it here. There it is, right there on your view. Okay, so about halfway up the celestial sphere. So let's back. And again, these will be on the exam, so just play around with this. So that was lunar eclipses. Well, there's also solar eclipses. Solar eclipses are really rare, and they only happen in any one place on the Earth. They only happen once every 400 years. And remember, for a lunar eclipse, everybody on the planet sees it all at once. So that's why a lunar eclipse is not a big deal. But a solar eclipse is a really big deal because it cuts a very narrow swath on the Earth. There's Oreo cookies in the shape of eclipses, which is neat. So Mom, can you tell me what a solar eclipse is? No, son. Okay, maybe I'll just Google it. Anyway, like I said, astronomers are some of the world's funniest scientists. So here's a picture of an eclipse, of a solar eclipse. Okay, so there it is, that narrow little shadow that cuts across the Earth, travels at about 2,000 miles an hour. This one was an eclipse. I'm not familiar with that eclipse. There was an eclipse in 2017, in August of 2017. The previous eclipse on U.S. soil was 1979 on continental U.S. soil. There was an eclipse over Hawaii in 1991. I'm going to show you a video from there. The problem with the solar eclipses is that the Earth and the Moon are almost exactly the same size on the celestial sphere, but the almost exactly is important because the Earth goes around the sun in an elliptical orbit. We'll be talking a lot more about that. The Moon goes around the Earth in a very elliptical orbit. And so because these orbits are elliptical, you get closer and farther away from the sun and from the Moon. And so the exact sizes of the sun and the Moon do change a little bit. And because they change a little bit, the size of that shadow changes. And sometimes that shadow never actually touches the surface of the Earth. And that's what we call an annular eclipse. Also, the orbits are tilted, and we'll talk more about that in a little bit, which means sometimes the Moon doesn't go directly in front of the sun. It goes over an edge of it, and we call that a partial solar eclipse. So there's a total solar eclipse where the entire sun is covered, and that's the most impressive emotional experience that any human being can experience. And for those of you that saw not the partial solar eclipse in 2017, which was visible here in Raleigh, but the total solar eclipse, which was only visible if you went out to the mountains of North Carolina or you went someplace else in the continental United States. The total solar eclipse is just, it's very, very emotional. And every person who's seen it can tell you that. And so here are the two paths. August 21st, 2017, that was what they call the big eclipse. I was in a camp right there in Oregon. I know a lot of people who saw it in South Carolina, that little tip of North Carolina. And then in 2024, circle your calendar now, April 8th, 2024, we have yet another eclipse that's on US soil, and that's pretty much it for our lifetimes. Note that those two eclipse paths cross in Carbondale, Illinois, which is right there. Okay, they call themselves Eclipse Central. I would very, very strongly encourage you, for anybody that missed the 2017 eclipse, find some way to see the April 8th, 2024 eclipse. You'll all be out of school by then, hopefully. Here's a shot from a flight. I've got 3 eclipse videos. I'm taking the time with this because it's just so incredibly emotional.
Shadow coming in.
Oh yeah, there it is. There's the shadow. Wow, look at that. Here it comes. Oh my God, look at it. Here comes the shadow. Look at that. It's like a tornado. Oh my God, here we go. Here we go. Oh my God. Oh my God. Here we go. Look at this. Oh my God, it's coming. The moon's shadow is coming. It is coming. Oh my God, here it comes. Look at this. I've never seen it like this, ever. Only in a plane. No flashes. Oh my God, here we go. Look at it. Oh my God. Whoa. Look at that. Oh my God. Here we go. Oh my God, it's coming right over us like a storm. Look at this. Oh my God, we're getting close. Getting close. Oh, built the dome. I got Corona. There it is. Diamond Bailey's beads. Bailey's beads diamond ring. Look at that. Corona. Totality. Totality. Oh my God. Look at that.
Okay, so that was somebody I don't know. The next 2 videos I shot myself. This video I shot in 1979, hence the quality of the video. This is my sister there, who now lives in Mexico. And this is my son, who's now in his 30s and is a programmer in Champaign, Illinois, home of the Fighting Illini.
And you're not going to run up in front of the minister at church. I'm going to be scared if I yell at you, but I'm yelling at you too, because I love you.
This is in...
Oh, yeah. This is the best.
I want you to know I'm not going to hold this here until it goes totality.
But then we made this thing. It's like a giving to the god. It's a bunch of lava rocks with a pretty tea leaf right there. Then the clouds cleared away. Well, there was still a lot of clouds, but there was this one hole in the sky. That's where the sun stayed. So now we get to watch totality.
Who's got the other square?
I'm Neil Ford.
I don't know. Who's got the other welding square?
Who's got the square?
Where's my tea leaf? My tea plant.
It's gone. It's gone. Oh, look at it.
It's gone. Oh, look.
Look at it. Chris, we got the buses. You can look at it.
Oh, it's great. Oh, look at it. Oh.
You use these things now.
Yeah.
Wouldn't that?
Hello, this is Neil Fortner for DEF News.
Okay, and this video I took in the 2017 eclipse from an incredibly crowded place in Oregon. Oh my God. Anyway, that was, like I said, you really need to go see it. And you have a chance in 2024. So again, what matters is that the size of the sun and the moon are about the same size for when you're on the Earth. That could also happen on any other planet. And in fact, on Mars, it almost happens. Mars has two really tiny satellites. They're like 25 miles and 15 miles across. However, they orbit really, really close to Mars. And so the angular size, the size it appears on the celestial sphere, is not that different from the sun. And again, because Mars is much farther away from the sun is smaller. These satellites are much closer, and so they're almost the same size. As you can see with this picture taken by, I believe, the Curiosity probe. And that's what we would call an annular eclipse, which I just gave you the answer to the question. So let's skip the question. Best chance to see a lunar eclipse. Let's bring up the poll. And I haven't talked about this, but if you think about it, you can figure this out. Think about the fact that the takes a month to go around its orbit. Okay. So again, there's some confusion here, so let's take a look at it. Let's go back to, so here we've got, there's the moon, there's the Earth, and remember the moon takes 1 month to go around. So if everything lined up, there would be a lunar eclipse, and there's the solar eclipse. It takes 1 month to go around. So this would be week 1, week 2, week 3, week 4. And so here is a solar eclipse. When would be the best chance to see a lunar eclipse? And so let's do that poll again. Oh, I'm sorry, you couldn't see that because that's blocked it. So let me show you again. This is the solar eclipse, week 1, week 2, week 3, week 4. It takes 1 month to go around. So there's the solar eclipse. And so let's try that poll again. Are there better spots on Earth to witness a solar eclipse than North America? Yeah, just go to the web and you can find all the places that solar eclipses are happening within your lifetime. They happen all over the Earth, and so a lot of times there'll be cruises that will come, that will follow an eclipse path. You know, they go over every place, Antarctica, Africa, you name it. Really what you're looking for, though, is a place that is very dry so it has clear weather, which is why I went out to Oregon. Better chances. Okay, so you get a better answer now. And actually 2 weeks after and 2 weeks before are both valid answers, okay? Again, because here is, this is the solar eclipse. 2 weeks before, it would be there. 2 weeks after, it would be there, okay? So typically, solar eclipses, a lunar eclipse will happen 2 weeks before or 2 weeks after a solar eclipse. Okay, they follow that line. And in fact, let me show you another simulation while I have this up that makes that explicit. Okay, so the problem is that the Earth's axis is tilted with respect to the ecliptic, the plane of the line between the Earth and the sun. And so here is the tilt there described there. And as the Earth-Sun system goes around the orbit of the Sun-Moon system, Sun-Earth system, that tilt with regards to the line between the sun and the Earth changes, as you can see here. And so when that tilt is maximal, the sun, the moon's shadow is going to miss the Earth. But as that tilt lines up here, then you're going to see in the enlargement, it passes right in front of it. Okay. So it's the fact that the orbit of the Earth-Moon system is tilted with respect to the orbit of the Earth-Sun system. And only when those line up will we get eclipses. That's why we don't have lunar and solar eclipses every 2 weeks, and why they're relatively rare. Because, and this is actually pretty much to scale. Well, there's the actual size. You can see it's just a little pinprick. And so it really has to be line up very carefully. Okay. We can see this also in this graphic. No, not that one. Yeah, here we go. So let's see a solar eclipse. So here's a solar eclipse as the shadow of the Earth, of the moon goes over the sun. But note if we tilt the orbit just a little bit, and the orbit is actually tilted about 3 degrees, so it would completely miss in some cases. So that would completely miss, or if the orbit, if the moon happens to be at the farthest part of the orbit like that, then we're going to get the annular eclipse that we saw there. Okay. So again, that tilt, as you can see by that graphic there, matters. So let's go back to the keynote. Okay, so that's enough about eclipses. Again, I'll bundle up these simulations. Can you turn the speed all the way up? Not on this simulation, unfortunately. This simulation doesn't have a speed control. Okay. So now we're going to talk about what we call the geocentric universe and the heliocentric universe. The geocentric universe is common sense. The geocentric universe is the center of the universe is me, and when I look up, things happen around me. And this is our day-to-day experience. Nothing magical about it. And they said that the celestial sphere is literally a sphere that rotates around us. And that sphere includes various subspheres, the spheres that include the various planets and the moon and the sun. And so here is what we call the geocentric universe. It's also in the textbook called the Ptolemaic universe. So the Earth is at the center, meaning we are at the center, geo, Earth, center. And here's the planets and stars that go around us, which is great. So let me bring up a simulation. I'll show you that. The problem is the planets sometimes move across the celestial sphere, just like the sun and the moon move across the celestial sphere, but they don't do so uniformly. Every once in a while, a planet will stop and backtrack. Now, we don't see this in real time, but over the nights, every night you see Mars moves a little bit more to the east. And then all of a sudden it starts moving to the west, and then it backs up and starts moving to the east again. We call this retrograde motion. And let's talk about that in a little detail. So what you're going to see is a series of pictures of Mars as it moves across the night sky. So these are taken one night after another, okay? In fact, you can see the date there. So Mars on the night sky comes across and that. So for the ancients, the celestial sphere consisted of the fixed sphere of stars, and then it consists of things that move. And the things that move would be the the sun, of course, the moon, of course, and then what they call planets or wanderers, of which they knew of Mercury, Venus, Mars, Jupiter, and Saturn. There were other things that moved periodically, comets and asteroids. But for the most part, the celestial sphere was fixed. But they were very concerned about this weird motion of the planets, of the wanderers. And if we map that graphic, these images you just showed, this is the path it forms. It does this kind of a curlicue. And so the ancients tried to figure out, how can we model this so we can predict where the planets will be on the celestial sphere? And they come up with this ingenious model. And the ingenious model is Mars goes around the Earth, but as it goes around the Earth, it also circles around in what we call epicycles, okay? And what it's circling is nothing. But again, you can't blame them, because this is long before the concept of gravity. And so what they were just trying to do is create a mathematical model that described the universe, and they did superbly on it. And so this is the geocentric universe created by the ancients, Earth-centered. So we, the Earth, are the center of the universe, and it contains epicycles. The problem is that even with that circle, it wasn't terribly accurate. And so what they did is they offset the location of the Earth just a little bit, and they added an epicycle on top of an epicycle, okay? And in fact, towards the end of the geocentric universe, and the geocentric universe was the way we described planetary motions for 2,000 years, they had epicycles on top of epicycles on top of epicycles, okay? As you can see by this graphic here. And that meant that calculating the positions of the planets became very, very complex. Okay. So that was where things stood for 2,000 years. Then we got a guy called Copernicus. And these are the 5 dead white guys that you will be responsible for. There's a lot of other dead white guys. Our history is littered with dead white guys, millions of them, actually. But these are the 5 I care about for this course. The first one is Copernicus. And notice the timing here. Copernicus was alive around 1540s. Then we have Galileo, Brahe, and Kepler, who were contemporaries. They were all alive at the same time. And then we have Newton, who was about 80 years later. These 5 revolutionized our view of the universe. And the fact that they all happened about the same time is kind of just a miracle. By the end of the Newton era, we pretty much understood everything we need to know about the solar system and about the universe. And that view basically went unchanged until Einstein. Okay, so this was just an enormous intellectual ferment. Copernicus was the first, and he was the first to come out with what we now call the heliocentric theory. It's also known as the Copernican theory. Not really a theory. I mean, it is the way the universe is made. The heliocentric universe, instead of having the Earth at the center, he had the sun at the center, which made no sense because we're here, we're at the center. The reason Copernicus did this was because he thought it made the mathematics a lot easier. He didn't actually believe the sun was the center of the solar system or the universe at that time. He just thought this was a mathematical trick. And not only that, but he didn't really want to fight the church. And so he actually didn't publish this theory until after he died. Were Brahe or Kepler criticized as heavily or jailed like Galileo? No, they weren't. And that's because what they did was just considered mathematical. It was Galileo who really was a direct frontal attack on the church. We'll talk a little bit more about that in a second. And so here, the problem again was this, what they call the retrograde motion. And in the heliocentric universe, the retrograde motion follows out naturally, because when you have 2 planets orbiting the same thing, as one planet passes the other, you very naturally get that retrograde motion. Okay. So here it is, and that's true both for planets like Mars, but also for internal planets like Venus. Okay. So as long as you have two bodies orbiting the same thing, retrograde motion follows out. And it's nothing special. You don't have to put epicycles, and you don't have to put epicycles in front of epicycles. Now, it took almost 100 years for people to accept Copernican theory. Part of that delay was because the church felt that it was against church policy to talk about this, even though it's not in the Bible. But part of it was that Copernican theory, in terms of predictions, wasn't as good as the Ptolemaic universe, the geocentric system. And that's because the geocentric system had 2,000 years of mathematical refinement behind it. They had all sorts of bells and whistles to really refine those predictions. Whereas the Copernican theory was just a kind of a nascent theory that just had planets orbit the sun. And the main problem that Copernicus had was Copernicus had these orbits as circular. Well, we now know that none of these orbits are circular. Some of them are close to circular, but they're all elliptical. And because they're elliptical orbit, their speed changes. And because their speed changes, it would make a mess of any prediction where you thought that they were circular. Okay. So we also call this the Copernican Revolution, although Copernicus was not alive to see it. And the Copernican Revolution was really saying, yeah, this isn't a mathematical theory. This is actually describes what the universe is really like. We really do orbit the sun. The sun is really the center of our solar system. Now, they didn't know at the time that the solar system was just one small part of the universe, but certainly the sun is the center of us. We don't occupy a particularly special place in our solar system. Okay. We are not the center of the universe. That's what they call growing up, actually. When we're born, we're the center of the universe. As we mature, we discover that we're just one small part. There's something called the Copernican Principle. This is something that Copernicus had never espoused himself, but we use the fact that Copernicus took us from the center of the universe and put us off to the side. And the Copernican Principle is the following: we do not occupy a special place in the universe. Every time we learn more about the universe, we discover that we're less and less special than we think we are. We are not the center of our solar system. We're not the center of our galaxy, and we're most definitely not the center of the universe. It appears that way because that's our observation point, but it's just not true. Okay. We'll be coming back to the Copernican Principle, especially towards the latter part of this course. Okay. So now let's talk about Galileo. And again, we're coming up to the 1600s. So Galileo, you're all familiar with Galileo. You know, he was the first one to use it. Telescopes existed, but Galileo was the first one on the planet to use a telescope for astronomical observations. And then we have Brahe and Kepler, who were really just mathematicians. And that's why they didn't get persecuted as badly as Galileo. He lived in the 1500s, 1600s, did not invent the telescope. He did use it to confirm the Copernican model. And he said so explicitly over and over. He said that his observations confirmed that Copernican model wasn't just a mathematical model, it actually represented reality. And that was a real threat to the church. The Bible tells us how to go to heaven, not how the heavens go. Okay. So the first thing he did is he looked at the moon, and like I said, you can, since our resolution is only about 1 arc minute, and the moon is about 30 arc minutes across, our ability to observe the moon visually is relatively poor. However, with this telescope, he could see that the moon consisted of valleys, it consisted of craters, it consisted of mountains. In other words, it wasn't a featureless orb. That was strike number one. Strike number two, he saw satellites orbiting Jupiter, okay? And at least Jupiter conformed to the Copernican model of satellites orbiting something. So that was strike number 2. And there are pictures using a reasonable telescope showing the Galilean moons. You can see the Galilean moons of Jupiter with just a pair of binoculars. You don't need a big one. Are there any astronomers or philosophers of modern times who made anywhere close to contribution as these dead white guys? Absolutely yes. That would be Albert Einstein. Albert Einstein and Isaac Newton are 2 of the greatest human beings that our planet, our civilization, our species have ever generated. Okay. And I would say that Einstein's model of the universe is as revolutionary, if not more so, than all those 5 dead white guys. So those are the 2 things. The third thing that he did was he said that Venus had phases. And that was revolutionary. And that was actually the nail in the coffin of the Ptolemaic version. And let me show you that in a second. Okay. New share. Safari. Okay, so here is the Ptolemaic version of the Earth, the Sun, and Venus. So on the Ptolemaic version, the Sun goes around the Earth, okay? Sun goes around the Earth, and Venus orbits on an epicycle on a line between the Sun and the Earth, okay? And here is the graphic of what you would see if you could look up at Venus close up. Now, of course, without a telescope, you can't see this. But with a telescope, you can see the phases. And notice in the Ptolemaic version, the geocentric version of the universe, those phases, they get to not quite half, and then they get to new, but you never get a full phase, okay? You only get partial phases, okay? Whereas let's contrast this with the Copernican version of the universe, where we have the Sun and Venus and Earth, and Venus goes around the Sun and Earth goes around the Sun. And note, here is the phases of Venus as seen from the Earth. And note, in this case, Venus goes through all the phases, including having the entire side illuminated. There is no way that you could see these full phases of Venus and continue to say that the Ptolemaic version of the universe is the correct one. So this was the nail in the coffin of the Ptolemaic universe. The problem was he made this observation with a telescope. And again, the telescope was a brand new instrument and people didn't trust it. And people thought there must be something wrong with the telescope. And this is not an old argument. This happens today. You know, when we do simulations of hurricanes, for example, people don't trust those simulations because it's a new simulation, for example. Okay. So that's what Galileo did, and that was by the mid 1600s. Pretty much all people knew that the sun was the center. Although it wasn't until Newton that we really understood why that is. Okay. Other questions? Oh, I think it would be possible for a certain lineup of the planets would be possible for a spacecraft to use the gravity to slingshot. Yeah, the Voyager mission did that. In fact, most deep space missions use the slingshot effect. And that lineup of planets only happened in 1970s, and I think it'll next happen in another couple hundred years. The telescope is a lie, that's correct. Okay, let me do some questions here. Okay, a total lunar eclipse occurs. Okay, and that's correct. It happens during the full moon, as you could have seen by that by the simulation I did. Okay. Stop sharing. Concerning the moon's phases, everyone on the Earth sees. And what they mean in 24 hours is within, the same short amount of time. Okay, and that's correct. So we all see the same moon. And so the moon, depending on your location on the Earth, you're going to be visible at different times, but it's going to be the same phase. And they say 24 hours because, different people in different parts of the Earth you can only see the moon at night, and you have moon at night at different times. We definitely do not see different sides of the moon. We all see the same moon. Okay. A solar eclipse happens. Oh, let me change the sharing. Sorry about that. We actually didn't talk about this, but this is important. Okay, I'm impressed. You guys did pretty well considering the fact we didn't talk about this. And the answer is every 6 months, and let me show you why that is. So here is a graphic showing the tilt of the orbit of the Earth moon system compared to the orbit of the Sun-Earth system. And so when that plane is tilted like here and here, you really can't see an eclipse because the moon is above or below that plane. It's only when you've got this sort of orientation here that you're going to get the planes line up, and possibly the shadow of the moon will pass over the Earth. And that happens once every 6 months, okay, as we go from there to there. So again, we didn't see it, but most of you guessed correctly or figured it out correctly. So that's impressive. Okay. Next question. Actually, this will be the last question. Mars, Jupiter, and Saturn show retrograde motion because and again, this is another question we didn't really cover. The speeds of the planets, as we'll be talking about next time, changes as you go out. So the closer you are to the sun, the faster you move. And so Jupiter and Saturn move very slowly compared to the Earth. And so as the Earth whizzes by inside the orbit, it speeds up and passes by Jupiter and Saturn. Okay, so you mostly got that right. Okay, that ends the lecture part of the course. Let's see, Louise? Oh, you can turn your mics on now. So I thought a solar eclipse happened every 400 years. So yeah, let me explain that. The system is favorable for a solar eclipse once every 6 months, but it doesn't mean it happens every 6 months. It's just because the moon has to be in exactly the right place, even though it's favorable for that. And so the solar eclipses only happens about once every year or two. However, on a place on the Earth, it happens once every 400 years. Because that eclipse path is so narrow, it only cuts a small part of the Earth's surface. Okay, so let's go down. From the video showing the planets as close to the moon, are there solar systems where the planets orbit that close? Or would those two bodies be too massive to not collide via gravity? So yeah, there's a system we'll talk about towards the end of this course called Kepler, I'm sorry, I'll look it up, Kepler 7, I believe, where we do have planets that are orbiting very close to each other, as close as you saw. If they're close and big, yeah, it's not a problem. But if one of those planets is Jupiter, they will mostly be kicked out. And solar systems over hundreds of millions and billions of years tend to be very unstable. Okay, we'll talk about more when we talk about orbits. Let's see. Can you describe a blue moon? How common is this? A blue moon is really I think that's a human artifact. The blue moon is where you have 2 full moons in 1 month. Can somebody look that up while we're doing it? I think that's correct. Let's see. How is it that the moon's orbit around the Earth changes if the Earth's precession takes time to occur? The moon's orbit around the Earth is elliptical, and so the distance between the Earth and the moon changes from month to month, okay? The precession happens over tens of thousands, and that's a very different effect. The precession doesn't affect any orbits. It just affects the tilt of the Earth's spin relative to the ecliptical plane. When will the next eclipse be? After 2024? On US soil, not in our lifetimes. So if you want to see an eclipse other than 2024, you're going to have to travel to a different country. What is your favorite moon phase? Oh, full of. Can you explain blood moons a little bit more? I don't know that. So it's not an astronomical concept. That's a human concept. How will these cycles be affected if one of the planets was moving in the opposite direction? We would not be here. First of all, there's something called conservation of angular momentum that would violate. The only way that could happen if we had a massive eruption of our planetary system by, say, a near miss or a collision with another solar system that just created chaos. And a planet orbiting in the wrong direction would last, I'd say, less than 1 million years before the whole system went nuts. It would just create too much chaos. What would happen if a person went into space with no proper protection? People have studied that, and you would actually be able to live for probably close to a minute before you died a horrible death. Your blood starts to boil. You essentially get the bends, but people have survived the bends. A bends is when you come up too fast from scuba diving. You get little nitrogen bubbles in your blood, and those nitrogen bubbles cause problems in other places. And the same thing would happen in outer space if you're exposed to a vacuum for more than a few seconds. But it's exactly like the bends. You're just changing the pressure. Eventually, your blood would boil. You'd get all these sorts of things, and then your body would freeze, and it would be a bad day. What causes everything our solar system to rotate counterclockwise other than clockwise? Yeah, that's a good question. If you remember, I showed you that video early about why our system is flat. The reason why, and so our entire solar system was born with a certain momentum. The angular momentum it was born with is completely random, okay? And randomly, it's not going to be born with 0 angular momentum. It will be born with some. And that angular momentum has a direction. And that direction that it's born with will then decide the direction that everything rotates. The direction of that rotation relative to the Milky Way galaxy is random. So every solar system in the Milky Way galaxy rotates in a completely different direction. We use counterclockwise just because by convention, we're always looking up at the solar system from the top down, okay? If we had a different convention, if we always looked at the solar system bottom up, then we would say it always rotates clockwise. Can you explain an annular solar eclipse again? An annular solar eclipse is a total solar eclipse, but the moon is a little smaller than normal and or the sun is a little bigger than normal, so the moon doesn't quite cover the sun, and you get this ring around the moon's shadow. What is a blue moon? I don't. Based on the information in the textbook, what specifics should we make sure we know about the history of astronomy and all the different people and what they discovered? I will send out, as I mentioned in the syllabus, I will send out a PowerPoint before the exam. In fact, I'll make it up this weekend and put it and post it, that will list the exact topics that you will be responsible for on the exam. All the exam questions, with the exception of the questions I add in the lectures, which I forgot to add for this lecture, sorry, are the textbook. But in general, there's only 5 guys who you're responsible for, the 5 I listed. Nobody else you'll be responsible for. Why are special glasses necessary for solar eclipses? They're not. Special glasses are necessary to look at the sun, okay? So if you want to look at the sun without burning a hole in your retina, you need special glasses. It has nothing to do with eclipses. But it's only during eclipses you want to look directly at the sun and see that the little crescent shapes are. Now, during the total solar eclipse phase, you don't need glasses. Everybody can take their glasses off. In fact, you want to take your glasses off because it's fairly dim, okay? How do gigantic moons appear? How close to the Earth is for it to appear that large? So what you're talking about is the moon seems to be at different sizes depending on the night. And a full moon right at the horizon appears huge. But you can measure it. It is exactly the same size. You can put up your thumb, compare the moon size to your thumb some night when it's on the horizon and directly overhead, it will be exactly the same size. So it's a psychological effect, not a physical effect. In North Carolina, was a solar eclipse we saw in 2017 a partial one? Depends on where you were. If you were in Raleigh, yes, it was partial. If you were in Western North Carolina, you would have seen a total eclipse. They were really lucky. The Great Smoky Mountains, they actually saw it, where according to weather, they shouldn't have been able to see it. Why is gravity of the moon so different from Earth's gravity? We'll be talking about that 2 lectures from now when we talk about Newton and gravity. How can you tell what phase of the moon is the longest and what is the shortest? Same size, by tradition, okay? How long is a day on the moon? Well, Gracie, how long do you think a day on the moon would be? A day on the moon is you go from sunlight to dark, back to sunlight. You should be able to figure that out. And anybody else, just answer Gracie in the chat. Questions 13 and 14 on the assignment are the same but have different correct answers. Ward, I will look at that. And that was the homework due today, right? We have a study guide for the first exam to narrow down specific sections of information to be sure to know. Yes, you will have a study guide. I'll post that this weekend. Why does the moon change colors when it's visible at night? That's a very interesting question. The reason why is that the moon surface, when it's dark, is illuminated by the light that goes through the Earth's atmosphere. So if you look at the moon, at the Earth, when it's from the dark side of the Earth, what you'll see is the Earth mostly looks dark. Light in the center of the Earth from human lights, which is a very, very minor part of what illuminates the moon. But what really illuminates the moon are the sunsets that circle the Earth. And it's those sunsets that create the light that we see. And that's why the moon, when the moon is dark, we mostly see red in the dark part of the moon, because that's from the Earth's sunsets. Now, the exact color of those sunsets will vary from time to time. So whatever phase the moon is in the Earth would be the opposite of that phase. For instance, would be right to say the moon is in the waxing crescent, the Earth is in gibbous phase. I believe that's correct. I hadn't really thought about that. And then you're certainly not going to be quizzed on that, but that's an interesting observation. What effects do you think the moon would have on us if we were by the moon? Do you think it's just the same? Or were we not at that angle? So the moon is locked into always having one face towards the Earth through what we call tidal locking. We'll talk about that when we talk about gravity. The moon is a little lopsided, and so the loppy part of the moon is, it's heavier and it's kind of fixed towards the Earth. And so that means that the moon rotates once a month. By the way, that's the answer for rotates once a month, but that once a month is also exactly equal to the orbit, and so it's always facing one side. The far side of the moon, it's pretty much the same. We first photographed it, 40 years ago. It doesn't have those dark areas that the near side does. So from a far distance, it pretty much looks the same as the near side, the side that we see. If we look up closer, it's actually very different. We think that's because the near side has had massive collisions and the far side has not. Could the moon ever float away if our gravitational pull weakened? No. There is no, if gravity could change, that would be a radically different universe than the one we observe. So we observe the entire observable universe by definition, that is 77 billion light years across. Nowhere, anywhere have we ever observed gravity weakening or strengthening. If that ever happened, we would see it and we would know that the universe is a wild, mysterious place. That's not the universe we live in. The universe we live in is where gravity is fixed. Have any of you studied chaos theory? Well, hey, I watched Jurassic Park. So yeah, the chaos theory, we don't talk about that in this course, but it's very important when we're talking about the orbits of planets and exoplanets, because solar systems over millions of years are chaotic systems. And the fact that our solar system has been stable for 5 billion years is just frankly a miracle, and that's why we're here. What would be the chances that the Earth is struck with solar random effects? So if the Earth, we are hit with solar storms periodically. There was a great solar storm in 79, that took out the Canadian power grid. There have been other solar storms where the sun sends a huge swath of charge towards the Earth, and they get through our Earth's magnetic field shielding. In 1859, the Earth was we call the Great Superstorm, or the Barrington effect. The Great Superstorm wiped out telegraphs worldwide, and it created aurora borealis all the way down to the equator. They were visible every night in North Carolina. They actually electrocuted one person that was working in a telegraph office when the charges from that great solar superstorm hit a telegraph line. Other than that, it really had no effect because the Earth was not electrified then. Today, we're surrounded by power grids, and we're critically dependent on power. And those power lines are thousands of miles long. Those power lines will absorb the charges from a superstorm and produce surges that will blow out the transformers and the relays on all power grids worldwide. So if we had an 1859 superstorm on the Earth now, it would wipe out power across the world for months to years, because it would take years to rebuild all the transformers that would be blown up. And so the question for you all is, can 7 billion people survive for 6 months with no power? Think about that a second. So first exam, September 3rd. When doing the small angle formula, the textbook would round the nearest energy, or Webb sign will do that around a couple of digits. Yeah, so WebAssign should accept rounded answers, and if it doesn't, please let me know. And that's another reason why you should do the homework early, so I'll have time to correct that. The day on the moon is the same as the sidereal period, I believe. Very cool. I've read it much more up on chaos theory in my free time. So chaos theory is a very important theory, and for lots of things in astronomy, and the thing that would most apply to the course is planetary orbits, but it also relates to the formation of galaxies. And so I'm out of time. Thank you very much, and I will see you all on Tuesday. Thanks a lot. And this is okay. Stop share. Bye-bye.